Hola amigos, welcome back. We just finished our first exploration of an authentic real-world modeling problem that gives rise to a standard eigenvalue problem. That was the couple pendula problem, and we use the McCusker apparatus as an entry point to transform a measurable phenomenon, something that we could observe and measure, into an algebraic problem of the form square matrix A, unknown vector x, unknown scalar lambda. For that given matrix A, find all eigenvalue eigenvector pairs such that A times x is equal to lambda times x. I do want to reiterate that eigenvalues and eigenvalue theory is really kind of a second part of linear algebra. Specifically, we spent a ton of time. In fact, the majority of our introduction in linear algebra was on the first problem type, which takes the form known vector A, right-hand vector B is known, and we want to find all values of x such that A times x is equal to B. This problem I would call a statics problem if I was an engineer. As a mathematician, I say it's a problem involving algebraic equations, but the idea is that we are measuring properties, we are trying to solve for something that exists without time. Another way to say this in the context of real-world modeling is when I'm solving the problem A times x is equal to B, that's equivalent to taking snapshots in time. So I take a picture at one time, I look at properties of that picture, I let dynamics play out, then I take a picture at a different point in time, and I compare the first picture to the second picture, and I ask myself, what are the differences between the things that I'm observing at those two specific instances in time? So imagine throwing a ball in the air. In the first picture, I take a picture of the ball right as it's being thrown. And the second picture, I take a picture of the ball when it's at the top. And then I ask myself, what's the difference in height in those two pictures? Those are algebraic equations because I'm not trying to solve for the entire path of the ball, only for the differences in position at discrete points in time. Our approach to linear systems problems as well as least squares problems really focused on how to solve this problem algebraically. As we transition into the eigenvalue theory, or the second major problem type in introductory linear algebra, the main idea is to have tools to deal with what we call differential equations. An engineer might call those dynamics problems. The point of those is to take problems that exist in the real world that change over time and turn them into algebraic processes. Now, in our analogy, if algebraic problems are equivalent to studying snapshots in time, differential equation problems or dynamics problems are equivalent to looking at movies, sequences of events that play out over time. And when we solve those, we don't just want to talk about the differences in two time periods. We actually want to create a function to model the entire behavior or phenomenon over that movie. So as time plays out, can we model what's happening in the sequences of images that are captured in the videos? Those two problems kind of fit nicely into statics and dynamics. One of my major goals is to help you get a big picture view of what's happening in this theory. So as you suffer and focus on studying the small detail, the minutiae of this theory, you can make explicit connections between the hard-won knowledge and wisdom that you're building for specific technical content with a much broader view of this theory, and start to prepare yourself to apply this theory in action if you'd like. With that in mind, let's return to the commutative diagram of how eigenvalue theories get applied in practice. On the left-hand side, we'll focus on the idea of dynamical systems, or as a mathematician would say, differential equations. The whole idea is that we start with a real-world problem. In the couple pendula problem, that was two pendulums swinging that are connected together with a spring. That involves a continuous dynamic phenomenon, something that changes over time. In our case, we want to figure out the position of each mass on the end of each pendulum at any time during an observation. The solution of that would be a function to describe that, or the ability to pinpoint the exact location of that mass during any time in our observation. Going from looking at the problem to having that solution is not an easy thing to do because the human eye can't slow time down, and usually those dynamics occur quite quickly. The idea of the mathematical modeling process is to translate that real-world problem, a continuous problem, into an algebraic problem via the process of mathematization. For the couple pendulum situation, we actually spent a ton of time mathematizing. That is a small introduction to the cost, the actual work and intellectual effort required to translate meaningful problems into mathematical problems. It is non-trivial. We're going to talk about that in just a sec, but I do want to call that out. Once we have our ideal mathematical model for the continuous problem that we started with, in this case in the form a times x equals lambda times x, and we're searching for scalars lambda and vectors x that satisfy that, we then do mathematical analysis, which is basically applying the theory that we're supposed to learn in math class, the stuff that math class is really focused on, to generate a meaningful solution to our ideal problem. Once we have those meaningful solutions, so in eigenvalue theory, that would be eigenvalue and eigenvector pairs that solve that original problem. The claim is that we should be able to, if we're lucky, interpret and verify that our solutions give us meaningful insights to the original solution that we wanted for our real world problem. With this process in mind, I want to make a few remarks. Number one, mathematizing problems is non-trivial. In fact, it's usually one of the hardest parts of the entire process. Number two, most math teachers do not teach this entire thing in their classes. What they'll do is they'll focus on a subset of eigenvalue theory that is useful for introducing the major ideas. And then the goal is that you fill in all these other details to make this useful in your own life, which often requires years of intense study and intuition on how to find information in classes to help fill in all these pieces. I personally believe that's a bad model. I think we can do much better. In order for us to understand what the theory that we're learning means, I think we should actually spend the time as instructors and as educators to help you piece together the entire puzzle while you're being introduced so that you have motivation to understand why this theory is important and to really dive deeply. That's what I'm trying to do in this course. Moreover, mastery over theory is a long, arduous process. We will just begin that in this introductory course. But in order to get to a place where we're ready to apply this, it's going to take a lot more than just an introduction. We have to get deep into the weeds. Another way to say this is that eigenvalue education is nuanced and subtle. It takes a lot of time. To help us get an idea about how this works, I want to map that over to an analogy about the study of human mobility. So specifically, in order to get an idea of what we're doing in building eigenvalue theory, we're going to tell the story about how humans learn to move about the world, and then we're going to make direct connections between the different stages of that story and the work that we're going to do introducing eigenvalue theory. When we think about human life, we say usually a single life begins at birth, and sometime after that, that baby learns to crawl on their hands and knees. It's a slow process. They stumble. Eventually, that baby gets to a place where they're confident on their hands and knees and they're ready to take their first steps. That's where they begin to walk standing up. After they've done that for quite some time, they start to move a little bit faster, learn how to run and jump and move quickly. This process is really the foundation of human mobility and really sets the stage for more advanced movement. Specifically, after we learn how to master our own bodies, humans are amazing in the sense that we start to bring in larger technologies to allow us to move. That might include the ability to bike, to pedal, to ride a scooter, to skate. Technologies that are really designed to get us to move around faster and do require some mastery of the less technical aspects just involving the body. In the modern era, we then move from human-powered mobility machines to automated machines like cars, buses, vans. Those allow us to move around a lot faster, but they also require a huge upfront cost in order to get into those. After that, we have what we call the pinnacle of motion for most human beings, which is flying on commercial planes. Now, if I was going to walk down the street to a store, I don't need to get in an airplane in order to do that. But if I want to move around the world, if I want to solve a big motion problem, these type of tools are actually indispensable for being able to do that quickly and efficiently. Now, There are some humans that use specialized vehicles to get around, like astronauts will use a specialized vehicle called a spacecraft. We have people that use helicopters. We have people that use dirt bikes. We have tanks and all of the specialized equipment that get into technical applications. Now, I'm going to claim that the process of becoming mobile in human life is analogous to the process that we're going to learn in eigenvalue theory education. So specifically, I would say that life begins at the moment that we're introduced to our first eigenvalue problem that makes it different in the world. There are some mathematicians that won't even talk about this in their classes. They'll literally just skip the idea of applications and go right into theory. But as Dan Mayer says so well, if mathematics is the medicine, what's the headache? In order for us to understand how to move, in order to understand how the theory actually applies, we have to have the intellectual need for that theory. And that, in my opinion, means we need to know where eigenvalues show up in our own world. Once we're born into the space of needing eigenvalue theory, my claim is the first step in order to learn to crawl, to move around on our hands and knees, we need to know how to solve small problems by hand using pen and paper analysis. The reason is we want to start to set the foundation for more complex problems by getting our head around how these things work using our own brains. Once we've studied our first few problems by pen and paper analysis, maybe 2x2 and 3x3 matrices, that's where we start building an understanding of and fluency with basic eigenvalue theory. At this point, we're ready to really apply eigenvalue theory for small-scale real-world problems, and I would call this the end of the introduction to eigenvalue theory and the beginning of our more advanced stages of life. This is the end of single human mobility based on the body and the start of bringing much more powerful tools to bear on harder problems. We're not going to spend a lot of time talking about that in the introductory class, but I do want to call those out so that you understand what you're doing when you set the foundation in eigenvalue theory for future possible applications. When we make the transition from introduction to more advanced theory, I believe that the first phase of that is to find larger problems that eigenvalue theories apply to. That would happen in advanced engineering and technical classes, as well as on-the-job training in engineering firms. Once we have those larger problems that can be solved using eigenvalue theories, that's where we start getting into what we call specialized eigenvalue software libraries. And this is where the need for computation comes in. There is a point at which the size of a problem overwhelms our ability to do hand calculations. Could you imagine if I had 50 pendula coupled with 49 different springs? If I were to try to do that problem by hand, I would die before I solved it. That's where we bring in much, much larger tools, which are the ideas of computation, so that we can leverage those tools to speed up the way that we solve those problems. Now, I would say when we refine those into commercial airplane style problems, very, very large problems, that's what we call finite element methods. And in fact, what I would say is within finite element methods, there are specialized communities of practice that require customized eigenvalue algorithms for very special applications. These are the spaces where professional engineers and mathematicians make a lot of money solving problems because they require real specialization and technical skills in order to solve problems on an industrial scale. The point of introductory linear algebra is get us to a place where we are familiar with the terminology and the ideas as well as the application. Once we have that, computational theory takes us from small scale to large scale problems, and then industry pays for mathematicians to be able to solve those large scale problems. This is why it's so important that engineers take prerequisite classes so that when we get to these larger problems, we have a foundation upon which we can build our understanding. I like this analogy for many reasons, and one of them is that as we move down in complexity, the more complex concepts are based on fluency in the previous steps. So the idea of early introductions actually sets us up for more complex abilities. And the same thing is true with mobility. As we get more and more mobile and aware of our own bodies, we become able to leverage more powerful techniques and tools to move around faster. Another way to say this is wrapped up in the idea we have to learn to crawl before we can walk. For eigenvalue theory, that means that we study the basics, we study the introduction before we get introduced to the more complex concepts. And the more fluency we have in that foundational material, the lower barrier to entry we will face when we go on to more advanced problems and when we go to apply those problems in practice. The last reason that I really like this is that mathematicians tend not to talk a lot about the birthing process, but it is the most fundamental miracle of life. Birth is really painful, and a huge investment of energy and societal resources go into making sure that that birth happens well. The same is true for eigenvalue problems. The painful reality of most eigenvalue theories is it is actually just as hard to create the problems themselves than it is to solve it. And at this point in life, it is actually more difficult to build meaningful eigenvalue problems than it is to write code to solve those problems. That is one of the untold stories of applied mathematics. Building meaningful problems is probably one of the most valuable things that we can do with our education, and it is one of the least taught things in formal classrooms. One of the gifts that I hope to give my students is insights into how to build specialized expertise and interdisciplinary knowledge so that we ourselves can create our own problems and bring those tools into the communities that we serve. This is my focus in helping you set the foundation to give you the best introduction and the best material that I can provide for you so that you can set a foundation that you can build future expertise on. In this case, I'm partitioning all of the steps to build that expertise into what I would call introductory material and advanced material. To get advanced material, you're going to have to go on to future courses and really seek that out in your education. For our situation, we've already got a sense of where eigenvalues show up, and we've studied an authentic real-world problem to do so, the couple pendula problem. For the rest of our introductory lessons on eigenvalue theory, we're going to fill out the rest of this material and show how to use that theory to solve our couple of pendula problem. The entire structure of our introduction assumes that we begin with a matrix, and then we're going to develop theory that will allow us to solve eigenvalue problems involving that matrix. With that in mind, our introduction to eigenvalue theory is going to help us answer some fundamental problems that arise in the mathematical analysis phase of any applied context. Some of those questions include: how does the algebraic structure of an n by n matrix relate to the eigenvalues and eigenvectors for that matrix? Can we get insights into the types of eigenvalues and eigenvectors that arise if we know information about the matrix itself? Next, we might wonder, if we are given a matrix, how many eigenvalues and eigenvectors does that matrix have? Is it guaranteed that we'll always have a full set of eigenvalues and eigenvectors for any matrix that we're encounter in practice? We're also going to try to explore what are the connections between the eigenvalue and eigenvector pairs and information encoded in that matrix? How are those things related to each other? And then finally, if we are able to generate eigenvalues and eigenvectors for a specific matrix, how can we use that information in applied problems? What type of insights do eigenvalue and eigenvector pairs give us about applying that information when we're trying to solve dynamical systems problems? Our introduction is going to focus on trying to get good answers to these questions to help us when we're trying to analyze problems that arise with a given square matrix for a real-world modeling problem. In the next video, we'll break down the different topics we're going to study in this introduction and get a little bit more specific to give a global overview of our strategies developing eigenvalue foundations. I'll see you in the next video.